Over 250,000 people visit Farnborough each year to witness outstanding flying displays and to see the very latest British aircraft put through their paces. A show like this can't be seen anywhere else in the world, and yet, because it has become an annual event, we're inclined to take it for granted. Accustomed to the modern aeroplane, few of us bother to think about the tremendous amount of work that goes on behind the scenes to ensure that Britain's aircraft today are the most reliable and safe in the world. A few of us may marvel when a new invention hits the headlines, and for a time the newspapers will remind us of the achievement of perhaps one individual whose inventive genius made it possible. But no single person today could design and build an aeroplane for operational purposes on his own. It takes thousands of man-hours and often as many people working in teams to get an aircraft safely into the air, and behind the majority of this effort lies Britain's Ministry of Aviation. This is a big organization. In fact, it is so large that many of the employees themselves do not realize how great a contribution the ministry makes to the aeronautical world. But research and development are not confined exclusively to aeroplanes. The work is spread over a much wider canvas. This aircraft is landing at Farnborough, the Royal Aircraft Establishment, where within the fence exists virtually a scientific city. Here, scientists and technicians work with office personnel and service people in a common purpose. Expert teams perfecting existing designs, designing future developments. But Farnborough has been on the job a long time. In fact, its history dates back to the early pioneer days of aviation. After the Wright brothers succeeded in getting a heavier-than-air machine off the ground, many others took up the challenge of flying. Samuel Franklin Cody, an American, came to Britain, and in 1908 at Farnborough he built this biplane and flew it successfully, making him one of the first true aviators in this country. If you visit Farnborough today, you can see the tree to which he tethered his plane when engine testing. It is preserved as a memorial. During the First World War, the Vickers-Vimy bomber was developed, and soon afterwards the Farnborough scientists were on the job trying out ways and means of refueling in mid-air, experimenting the hard and dangerous way in the sky. They were also concerned with safe flying. In those early days, a stall or a spin could prove fatal, and so scale models of the most up-to-date designs were tested in elementary wind tunnels, these experiments leading to the development of well-behaved aircraft. Their work sometimes took them to sea, but early aircraft carriers were dangerous places, particularly when arrestor wires and crash barriers did not exist. Even when hooks were devised, pilots sometimes had difficulty in landing squarely on the deck, and nasty accidents were not infrequent. But flying techniques could only be learnt the hard way. A slight error of judgment and you damaged your plane, although on most occasions you escaped shaken but unhurt. This accident, however, severely injured a ministry cameraman. But he is still working today, only now he uses a remotely controlled camera to obtain the scientific records which have contributed so much towards the development of safe landing techniques at sea. Experiments were then carried out to find the method of landing an aircraft safely without an undercarriage. The landing area on the flight deck was covered with large rubber sheets supported by air-filled cylinders, also made of rubber. For the initial trials, a mock-up deck was laid out at Farnborough, and it was a tough assignment for the pilot landing for the first time. And there are other tough jobs. Here, a man is deliberately blacking out during high-speed aerobatics, while a cine camera records the details. Apart from the obvious medical interest, these experiments paved the way for research into ways and means of protecting pilots from the pull of gravity, leading to the development of modern pressurized flying suits. When ejector seats were devised, they had to be tested under actual flying conditions. When something is new, it is often an unknown quantity, and sooner or later someone must try it out for the first time. The initial trials will be made with a dummy, but a dummy has no feelings, so an observer will volunteer to obtain a physical reaction. In peacetime, he may seem heroic. But in wartime, thousands of men volunteered to join the parachute forces, and the Royal Aircraft Establishment went in for parachute research in a big way. Hundreds of jumps were organized so that studies could be made of the various designs and techniques. And the ministry staff went with them to record all the necessary information and data, filming every drop from an accompanying aeroplane and every landing from the ground, even though there was a fair chance that somebody might land on top of them. But parachutes could carry many other things besides men, and soon techniques were perfected for dropping an amazing variety of objects accurately onto a specified area. The equipment ranged from landmines and supplies to heavy-duty army trucks, and every drop was scientifically recorded and analyzed. It was also necessary to devise better and more accurate ways of launching bombs and aerial torpedoes from fast-flying aircraft. And a study was made of their behavior from the time they left the aircraft until they reached their target. Sometimes they were made to explode on impact, and sometimes they were made to penetrate heavy concrete before exploding. It was no easy job trying to follow a bomb dropped from a high altitude, but the slow-motion cine camera records proved to be a most valuable aid in this particular field of research because they could show details that the human eye could never hope to see in normal circumstances on the bombing range. At Shoebury-Ness, there is a different kind of range, a high-speed rocket runway, and it is used, for example, to find out what happens when a modern gas turbine engine collides in mid-air with light debris or perhaps a bird, in this case a dead chicken weighing 2 pounds. A rocket is fired and a striking velocity of 300 miles an hour is achieved before the brakes are applied. The results of the collision can then be analyzed at leisure, and it can be seen that even though the turbine blades were protected by a steel guard, there was considerable damage caused by the impact. And it didn't do the bird much good either. Here, 60-pound high-explosive rockets were launched at a concrete runway to discover whether or not they would explode if they were attached to an aircraft during a crash landing on an airfield. After a series of tests of this type, it was established that a pilot would not be harmed by these rockets, as there was no accidental detonation caused by the impact or friction. In the west of England, beneath the Malvern Hills, the Royal Radar Establishment is located, and here research is carried out on the very latest techniques in the field of electronics and radio location. Radar, once a wartime secret, is a household word today, and yet few people realize the tremendous advances which have been made in the design of and the uses for this equipment. Nevertheless, despite apparently simple operation, the relays and circuits are extremely complex. Malvern was also the birthplace of one of the largest solid-surface radio telescopes to be built in Europe, the tool of a new science, radio astronomy, and the link between man and his space satellites. The Royal Radar Establishment has its own aerodrome at Pershore and a fleet of aircraft to carry out practical experiments under active flying conditions. Sometimes a helicopter may be required for a particular trial, or perhaps a Canberra, but the aircraft are not always suitable, and in this case the nose was too small for the test equipment. So a design team got to work and planned a new nose for the Canberra. It was made up with fiberglass so that it would be both strong and roomy, yet extremely light in weight. At the same time, the radar equipment was wired up and the plugs and cables were prepared. Then a Canberra was brought inside for modification. The old nose was removed and the new one carefully fitted into place and the equipment installed. Within a short space of time, the aircraft was back in service again. In research of this type, it is sometimes necessary to know how electronic equipment will stand up to very heavy pulls of gravity, or G, encountered in modern high-speed flying, and so a centrifuge is used. The G is increased with the speed of rotation, and the equipment is kept working throughout the entire run. At very high altitudes, conditions of extreme cold are encountered, and so an ionosphere chamber is used to create those conditions artificially, and it is then possible to test radar equipment at ground level. Today, crystals are becoming an important part of electronic developments. Here, research is carried out on the development of crystals in an air-conditioned laboratory. The development work of the ministry, however, is not confined entirely to the establishments, and here is a project developed by a headquarters branch. It is an ingenious device for towing aircraft across marshy airfields. This skid wheel transporter prevents the undercarriage from sinking into muddy ground and enables the tractor to pull a heavy aeroplane at a fairly rapid pace with comparative ease. A conventional tow would almost certainly end with either the aircraft or the tractor being bogged down. From time to time, something out of the ordinary is required, and ministry staff are often responsible for original designs which are almost unique. Here at Boscombe Down, an aeroplane is being driven into a field, only at the moment the machine is neatly packed into the back of the van. This is virtually a build-it-yourself plane, and it comes in 3 large bundles. The fuselage is made of wooden struts which are covered with canvas, and the simple undercarriage is clipped on and locked into place by these pin clips. The complete aeroplane can be assembled by only 2 men in approximately 1 hour. The engine is extremely light in weight, although it has enough power to carry a pilot and an observer for quite long distances and at a reasonably high altitude. The controls, including throttle and ignition switches, are all mounted on this tiny compact panel. Every part has been planned with the utmost efficiency, keeping the weight down to an absolute minimum, yet simplicity has been the keynote throughout design. This is the wing. It's made of rubber sections cemented together in a similar way to a wartime barrage balloon. It is an interesting fact that it was developed in the balloon sheds at Cardington, where the ill-fated R-101 airship was built over a quarter of a century before. But instead of gas, it is inflated with air supplied by a manual pump. It takes about 20 minutes to fill, and should a leak occur in flight, a pump will automatically maintain pressure. It is possible for one of the 2 men to drive home in the van, and if the other has a pilot's license, he can free the brakes, open the throttle to its fullest extent, pull the stick back, and take off with the utmost ease. He might even fly home to await the arrival of his companion with the mobile hangar or van. This machine could be the forerunner of the family plane for weekend flyers. But have we enough sky for them? Already civil and military aircraft are flying in ever-increasing numbers. How is it that they don't collide with each other? And how do the pilots know where it's safe to fly or what altitude to keep? They follow aerial roadways mapped out by radio signals, and they even have junctions signposted by radio beacons called fan markers, which light indicators in the cockpits. Within a range of 150 miles or so, ministry staff can be in direct contact with the pilots. And if you've come a long way in a jet airliner, you won't have much fuel in reserve, so they'll get you down as quickly as possible. But what about the slower planes? Well, they stack them up at different altitudes and bring them down one at a time in between jet landings. As a passenger flying into London Airport, you would hardly realize that your plane was only one of the 600 or more to touch down here each day. They come from all over the world, yet the traffic moves with the regularity and ease of a taxi rank. You'd be arriving at one of the major crossroads of the world, and you'd be one of the 4 million passengers who pass through this terminal in a year. As your pilot signs off, others arrive and sign on, while their passengers arrive by the busload. Some may only be going as far as Paris, others perhaps all the way to the Far East. For a few, it may be their first flight. While the passengers relax in the luxurious main concourse, their planes are being made ready. Over 60 million gallons of fuel are used here each year, and behind the scenes in the workshops, every aspect of maintenance is carried out. Some of the people here work for the Air Registration Board, while others may have been apprentices at another ministry organization, the laboratories of the Aeronautical Inspection Directorate at Harefield. Although apprentices are trained, the main work is inspection, which covers a very large field, from checking gears to testing the strength of metal bars by literally tearing them in half. These laboratories contain some of the most precise and up-to-date scientific equipment. To detect a hidden flaw in a metal casting, they use a technique similar to the one hospitals use when looking for broken bones. They take a picture of the casting by means of X-ray photography. Or, if the subject is a difficult shape, film will be attached to it and the exposure made by one of the byproducts of atomic energy, radioisotopes, and the rays give an even exposure all round. There are also laboratories where the Electrical Inspection Directorate can check standards and make insulation tests on components. Here, the operator is protected behind a shatterproof glass screen while he builds up the voltage to a point where the electric current creates a discharge. In another section, there is apparatus designed to test and measure almost every conceivable type of electric lamp. The majority of the work is undertaken for the Air Ministry and the British aircraft industry, and these inspection directorates make certain that aircraft components ranging from motors to landing lights are as reliable and safe as possible. Only a few years ago, night flying was a risky business, and although the glittering lights from a city could tell a pilot where he was, he still had to find his airport by compass bearings. Today, ministry staff take over the responsibility, using the latest electronic equipment to guide him straight to the runway. The approach lighting at London Airport was designed by a ministry scientist and named after him. The culvert system, as it is called, is so reliable that it has now been adopted by the International Civil Aviation Organization for use on runways throughout the world. During the winter months, however, there is an unwelcome hazard in the London Airport area: fog, and unfortunately it's a regular visitor. The ministry developed Fido as a wartime fog disperser, but it was expensive to run. Today, radar plays a big part in helping the pilot to bring his plane down, for although he may descend into an almost invisible world, there are others who can see and help him. He is in direct contact with the men in the control tower, who guide him onto the glide path by literally talking him down, even telling him, for example, when to lower his undercarriage. But this system only works when there is enough visibility for the pilot to see the runway at the end of his descent. Otherwise, he could not make a safe landing. Obviously, radar is not the complete answer to blind landings. So the RAE at Bedford are developing equipment which will land an aircraft entirely by automatic means. With this system, an aeroplane can fly itself onto the runway. The plane is controlled from the ground by electronics, and the runway approach is wired in such a manner that signals are transmitted which operate all the flying controls. The system is so efficient that the pilot doesn't have to do a thing. He could sit back with his eyes closed while the blind landing equipment controls everything from flaps to throttles, to bring the plane down safely and accurately to make a perfect three-point landing, thus eliminating one of the worst flying hazards. Today, flying is becoming as safe as houses, and the pilot's thumbs up means more than just an engine start. It means that the combined effort of the aeronautical world, from research to operation, is steadily solving every problem the pilot once had to face. But when you glide smoothly into the air in a modern jet-powered airliner, or gaze upwards as a flight of jet fighters thunder overhead, it requires some effort to bring your thoughts down to earth again to think about the invention and development of the gas turbine engine. A large research establishment was set up at Pyestock to further the work of Sir Frank Whittle, the man responsible for the design and construction of Britain's first gas turbine engine. And this is one of the very first jets. All the facilities required for this research work, including the most up-to-date engine test houses, are installed at the National Gas Turbine Establishment. Although the theory of jet engine design was known to the world in the 1930s, development was held up until a new metal, pneumonic, came along. Here, modern metals are subjected to extremes of heat and cold to see if they will withstand the tremendous stresses encountered in high-speed running. It takes power to test engines. These generators develop something like 350,000 horsepower, enough for a small town. It is easier to test an engine on the ground than in the air, and in the test cells it's possible to simulate flying conditions and check and record the performance of every single part of an engine. To obtain the information, hundreds of instruments, wires and cables have to be fitted, and these are fed through into the soundproof control rooms where the scientists can monitor the test runs in safety and comfort, working to carefully arranged programs. However, the problem of analyzing all the data shown on the dials and gauges is a formidable one. But an electronic computer works out in seconds calculations that would take a man 20 or 30 hours to solve. When an engine has to be tested in the air, it is mounted beneath this flying laboratory. Should a failure occur, the pilot can use the regular engines to bring the plane home. Many of Britain's prototype gas turbines were tested in this way, and some of these engines are now fitted to world-famous aircraft. What goes up must come down, so the old saying goes, but here was a startling conception, a machine flying without propellers, wings or fuselage, a revolutionary development of the gas turbine engine. The planners moved quickly ahead, and the next step was to build a fixed-wing aircraft which would take off vertically and then fly away in the conventional manner. This is the prototype of the airliner of the future, a completely versatile airplane capable of carrying passengers or freight rapidly to regions which at present can only be reached by the slower-flying helicopters. Because it can land almost anywhere, it forecasts perhaps the disappearance of conventional airfield runways. Today, however, they are very much in vogue, and the jet uses up a lot of runway in a short time. For the aircraft designer, it's a race to the skies. But high-speed flying means new fuselage shapes. How do these designers know what shapes to adopt? Part of the answer lies in wind tunnel research. The tunnels are designed to run at different speeds, and in some the models are watched on closed-circuit television screens. They use a lot of models. Each one is built to the most exacting scale dimensions and is patiently made by hand. They can test a new shape in a wind tunnel. Or they can plan modifications to an existing aircraft and learn how much the performance of that plane will be affected. With the aid of instruments, they can find out almost everything about the flying capabilities of a new design. But there are research problems which cannot be solved in the wind tunnels, and in this case, ministry staff traveled to Canada, where the winter conditions were ideal for experiments in de-icing helicopter rotor blades. An artificial cloud was produced by forcing steam through nozzles on this grid, while the helicopter was flown in the cloud until the moisture had frozen hard on the blades. It was a risky business for the pilot, flying almost blind as close as that to the grid tower. However, the tests proved worthwhile and some satisfactory de-icing systems were evolved. The helicopter was once a fantastic dream, yet today we are beginning to accept this novel form of flying as a common or garden event, and the aircraft manufacturers were quick to realize the possibilities of this method of flight, and now there is a wide variety of machines available on the market. Daily, new jobs are being found for vertical ascent aircraft. Here is a mating between two of the latest methods of flight, the piloted rotorplane and the guided missile. Guided weapons have moved into the front line of defense. They have also moved into the Farnborough Air Show. Once top secret, they are now so well known that even a schoolboy could tell you, for example, that this is a Thunderbird. But how did they come about? Between the two world wars, Britain pioneered a pilotless radio-controlled aeroplane. It was called the Queen Bee and was used as a target for anti-aircraft practice. Then, towards the end of the last war, rockets were developed. But once the pilot had aimed his plane and fired them, he had no further control over their flight. Scientists at Farnborough and other places were asked to develop a rocket which would fly with some form of guidance control. It would have to seek out its target and then follow it, despite evasive action, until it had achieved a kill. But the speed of modern aircraft had increased considerably, and in order to be certain of catching them up, the guided weapon had to be capable of extremely high flying speeds. This meant research into the realms of the unknown, the regions of supersonic flight. A number of methods of flight control were devised, and in this case, research produced an electronic eye which would lock onto the target and then give out signals which would activate a steering mechanism to guide the weapon, despite considerable maneuvering, until it destroyed the target. The missiles needed engines capable of very high rates of acceleration, so the Rocket Propulsion Establishment was set up at Westcott for engine research. Here were located expert design teams and the most up-to-date and fully equipped workshops. In the laboratories, scientists experimented with fuels, while in the engine test bays, the rocket motors were put through exhaustive static firing trials lasting many days. The scientists worked inside blockhouses, safe from accidental explosions, and viewed the performances of the engines through periscopes. They found that solid fuels were suitable for some engines, while others proved very efficient on liquids. But it was not an easy matter to calculate the correct mixtures at ground level, because these fuels react differently at high altitudes where there is less oxygen. With the addition of fuel tanks, the body of the missile was becoming very crowded, and there was still more to come. Telemetry equipment had to be designed and installed to radio back to the scientists as much information as possible about the performance of the missile and its equipment during flight, and the information had to be recorded for analysis at a later date. By now, space within the missile was at a premium, and so, where possible, miniaturization became the rule. The gyro, the heart of an aircraft's automatic pilot system, was adapted and reduced in size to fit into the cramped body to stabilize the rocket in the air. And the researchers had to make certain that all these components would stand up to the extreme temperature variations and considerable pull of gravity encountered in flight. They built test vehicles without warheads for their early trials, and these were transferred to Wales, where, near the village of Aberporth, a rocket firing range was set up on the cliffs overlooking the Irish Sea. It was complete with missile launchers and the very latest radar equipment to track and monitor the flights. After the missiles had been given a final check-over, their tanks were supplied with fuel. Then the next, and probably the most rewarding part of the research followed, the actual countdown and firing. In those early days, it was an exciting process with a sense of achievement as the missiles sped away. To make certain the rockets reached maximum velocity as soon as possible after takeoff, some of the missiles were equipped with additional rocket motors or boosts. And these were jettisoned after a short time, allowing the vehicle to continue on its way under its own power. Test vehicle after test vehicle was fired into the Welsh sky, and by now the government had handed over the job of missile production to private enterprise, and on the range the contractors worked hand in hand with ministry staff. The flights were programmed to test the guidance systems, and the rockets were made to steer automatically to predetermined flight plans. But as the number of firings increased, so the work began to lose its glamour. It became sheer hard slugging, and sometimes when things seemed to be going well, the unexpected took place, leading to heartbreaks and disappointments after the many months of painstaking work. But it was only to be expected, for this was a new line of research, and there was literally something new to be learnt every day. So they went back to the drawing boards, and some of the test vehicles were redesigned. And then they built TRIDAC, the largest electronic analog computer in Western Europe, containing something like 1,000 separate units with over 10,000 valves and a staff of at least 20 people to run it. With TRIDAC, they could study the chances of a missile hitting its target, measure rates of acceleration, or test guidance systems. It was even possible to design theoretical missiles and learn how they would behave. Models could be set up on the plotting table, and a miniature aircraft steered by an experienced pilot could take evasive action, while TRIDAC, flying the missile, would outwit him every time. And so, steadily, the rockets began to come under complete control, and it was time to try them out in the roles they were being designed to play. Target aircraft were sent up, and the larger missiles designed for ground-to-air attack were launched at them. And even without explosive warheads, they proved deadly to conventional aircraft. This is not a ship at sea. It is an ingenious device built on the cliffs at Aberporth to develop a method for firing guided weapons from ocean-going cruisers for the Royal Navy. Their weapon was christened Sea Slug, but there was nothing sluggish about it. All these missiles were fired out to sea, and although it was possible to recover a few of them, it was obvious that a land range had to be set up somewhere. But this could not be done in Britain. We just didn't have enough space. So a range was set up over 12,000 miles away in Australia, where the desert regions afforded plenty of room for land recovery. In fact, the Woomera range extends over 1,250 miles before the sea is reached. Here it was possible to attach parachutes to some of the missiles so that once the initial firing had taken place, they could be gently lowered to earth again to land intact on the desert. Mobile recovery teams were set up to drive out into this arid wasteland where only brittle mulga trees and a few kangaroos existed. The teams were linked to base by radio, and their vehicles were specially adapted to carve roads directly to the recovery points. Above the desert, there was plenty of sky, free from commercial or military aircraft, and here the air-to-air weapons were tried out. These miniature missiles were attached to modern fighter planes and fired by the pilots against radio-controlled aircraft targets, in this case a Meteor fighter. But it was an expensive business shooting down real aircraft. There is not very much to salvage by the time they hit the ground. So, to reduce the cost, the Australians manufactured a high-speed pilotless aircraft which was launched from a trolley and navigated by a crew who were located on the ground. They called it a Jindivik. For the attacking aircraft, they made wonderful targets, which could sometimes be recovered if the missiles did not possess a warhead or damage them too severely. By now, the years of research and development were paying off, and the missiles had reached a stage of thorough reliability in launching and attack. The three services had set up weapon trials programs, and the guided weapon had become a very valuable part of standard service equipment. Meanwhile, rockets were being fired for a more peaceful research. For the International Geophysical Year, the Royal Society sponsored the development of Skylark, a missile capable of carrying instruments to an altitude of approximately 90 miles to explore the upper atmosphere. There is no end to research, and steadily the missiles became larger and more powerful. Now it was the turn of Black Knight to sit on the Woomera launcher pad. This missile was to go higher than any previous British single-stage rocket, but it also had another very important mission to fulfill. It was going to carry a special re-entry nose cone into space. By now, enough had been learned to send rockets up to extremely high altitudes, but it was a very different proposition trying to get them down again. They generally burnt up like meteorites as soon as they re-entered the Earth's atmosphere. Black Knight was a beautiful job, and although nothing as large as her had been handled at Woomera before, she worked perfectly the first time. And shortly afterwards, she returned her nose cone to the desert teams. A wonderful achievement adding knowledge to a new science, the science of the future, the science of the skies and all that lies beyond. Yet this little star ascending into the night sky is but a small link in the chain of events which are opening the doors to a new heritage, man's conquest of space.